All right, and welcome to your instructional video of how to use R to perform an occupancy model. Now, today I'm not going to go in very deeply into the nitty-gritty of R, how it works, the basics of coding, things like that. You really need to take some time to learn R. There's a lot of resources available. Really look at the stuff that Colin sent out. Some of those instructional videos will be really helpful. Also, if you've never used R before, I suggest that you come to me or the TAs during our office hours so that we can help you get settled and really start to be able to understand and use R. I did really annotate my code, so you should be able to use it fairly easily. And so we're going to use RStudio, which is a wrapper for R. RStudio is a little bit more user-friendly, and it's set up in these 4 windows. We have the actual coding window, and this is something that you can edit and save and come back to later. You have the console, which is where we're going to pass commands to R, and R will process things, and most of the results are going to end up down here in this bottom console. Up here in the right-hand corner, we have the global environment. So as we make different objects, they're going to pop up and be stored over here. And then we have obviously a plot area where we're going to show plots, and also that we can get information about the packages that we're using. So one thing you'll probably notice right off the bat is that my code is in a bunch of different colors. So everything that's in this kind of gray color that comes after a # or a hashtag is annotation, and it doesn't mean anything. It doesn't tell the computer to do anything. All it is just me leaving notes either to myself or to you in the code, so it'll be easier to understand this later. The things that are in black are the coding pieces. Things that are in green are usually names. And we'll get through that a little bit more as we go on. So I always like to be really specific in my annotation. I like to name my code, what the date was when I wrote it, and also I like to give credit to whomever wrote the code. And I did write this from scratch. I'm writing my name right there. Something that will come in handy for you guys is that throughout the code, you'll see these 3 stars. And whenever you see those 3 stars, it means that that is a piece of code that you will have to change for your analysis. We're going to go through the analysis using the cat data, and it will be up to you to then go back through and do the analysis with the possum and the raccoon data. So you should only need to change a few lines of code to get the answers that we're looking for. So unmarked is not in the base package for R, so that means we're going to have to download these packages from the repository. You need to be attached to the internet when you do this. And all it does is someone else has written code that runs these models, and we're just downloading that code from the internet and using it so it's a little bit simpler. I'm not going to run these 2 lines because when you reinstall something, it'll actually make you restart R, and I don't want to do that. So just know that unmarked is where all the occupancy modeling is, and ggplot is actually to help you make nicer graphs. So once you've installed your packages, you're going to have to load the library, and you'll have to run this piece of code every time that you open R. And so we're going to load up all of unmarked, and we can ask if we want more information about unmarked, we just type the question mark and unmarked. So you can either, to run a piece of code, you can either press run or you can press Control Enter. I'm going to try to remember to press run so that you guys actually see it, but I apologize if by habit I press Control Enter. So when we ask for information about unmarked, it pulls up the help file in this console, and it just tells it that this is models for data from unmarked animals, which makes sense, and it has the occupancy model in it. It has a few other different extensions of the occupancy model. You can do distance sampling, you can do p count. So there's a lot of uses for the data that we collected from unmarked animals where you don't actually have an individual ID. But we're going to use that very first model that's listed in the package, which is just fitting the single season occupancy model. So let's get the information for that model. And we can see that OCU fits the McKenzie et al. 2002 occupancy model, which is what we've been working on the last couple of weeks. And it gives us some information about the things that we need. We need a formula and we need data. And we might use some other options that become more important as we get more advanced with occupancy modeling. But for now, we're just going to use the defaults in the model. And so we see that data needs to come in a very specific object. And so we'll have to create that in the next couple of steps. So let's load up our data. So the first thing that you need to do is you need to set your working directory, and that's where your data is stored. You will have to change this because your data directory will be different than mine. I actually will change this and show you how to get this location. So I've put all of my data into this occupancy folder. And you can see it just says occupancy data if I'm in the mainframe, but if I go up to the actual bar, it gives me this whole pathway, and that's what R needs. So I'm going to copy that pathway. I'm going to paste it into R, and for some reason, I'm not sure what it is, R does not like front slashes, it only likes backslashes, so we have to go back and fix all these front slashes to backslashes. Once we do that, we can run that piece of code, and now our working directory is set. So in here, I have the cat data, the possum data, and the raccoon data, but we're just going to run through the cat data. So we're going to read in the data by using read.csv, and I'm going to say cat.csv because that's the name of the file. Remember that R is case sensitive, so this has to be a lowercase c. And I'm using the header equals true command because it's telling R, when you load cat.csv, realize that the very first row are column names and not data. So we'll read that in. And there's the data. It showed up in our global environment. And we can look at the first 4 rows of that data to make sure it came in correctly. And that looks right. We have the sites. We have the presence absence information for each of the days. And then we have the lure, which is exactly what we wanted. So the first thing we're going to do is calculate naive occupancy. Remember, naive occupancy is just the total number of sites where you saw the animal at least once divided by the number of sites that you surveyed. So we're going to get a total for each of the rows, and then we're going to convert that into just present absent for each site, and then we're going to divide that by the total number of sites surveyed. And so what that shows is that for cats, our naive estimate of occupancy is 60%. 60% of our sites were actually occupied by cats. And we're going to try to change that estimate once we have a better estimate for detection. So we need to create an unmarked frame because that is what holds the data for the occupancy model to read. R can't just look at your data and know where your observations are versus your site covariates and things like that. So we have to tell R in a very specific way what we need. So you can yet again ask R for more information about the unmarked frame. And here it says that it's a way to organize your data for the single season occupancy model. And we need Y the site covariates and the observation covariates. And it looks like that we also have an optional place to put map info. So, and for what is Y? Y is our detection, non-detection data, and it's an R times J matrix. And so remember, R is the number of sites, and J is the number of sampling periods. So it's the number of sites by the number of sampling periods. Site covariates are the covariates that vary at the site level, and observation covariates are covariates that vary within sites. So that's pretty straightforward, and so we can make that unmarked frame. First, we'll get the Y. We'll go into data. I'll show you the data right now. We see we have 15 sites. Remember, we had to toss a couple sites because of that camera failure. And we just want to give the presence absence information. So we don't want this first column and we don't want this last column. So that's what we're doing. This is saying give us all the rows because this piece is empty. So it's all of the rows and just column 2 to column 8 because that's where the detection data is. It's 1. So it's 2, 3, 4, 5, 6, 7, 8. So we'll select the observations and then we'll double check that we did that correctly by looking at Y. And there we go. See, we pulled out all of the right observation data. We don't have the sites anymore and we don't have the lures. So now we're going to have to tell R where we want lure to go, and we want lure to be a site covariate because remember that's what differed between the sites in our study site and our study. Other things that we could put here would be things like habitat type or canopy cover, things that are different between our individual sites that may be driving the underlying occupancy or detection probability at that site. So we're going to create the site covariate, and there it is. It's the lure. So we see we've got all of the different site types. And the next thing we're going to do is we're going to make the observation covariates. And so observation covariates are the things that change by day, by how the different visits change. So what we're going to do is we're actually going to say that the actual day of the week might influence our detection probability. We're going to do it in 2 different ways, and I'm going to show you how to do that later. We're going to say that day is continuous and that the day starting when we placed our bait had the highest probability of detection, and that detection probability faded throughout the week as kind of that bait dissipated into the environment. We are also going to say the alternative hypothesis is that day doesn't really have any structure and every single day has its own individual detection probability. Monday might be different than Friday, which is different than Tuesday. But to create that, we need to make a R times J matrix, which is what we've done. So we have 1 where it's for the first day, 2 for the second day, 3 for the third day, 4, 5, 6, 7, so on. So now that we have Y, we have our site covariates, and we have our observation covariates, it's time to actually create our unmarked frame. And so there we've created it, and it popped up over here, and you see that it's a formal class of an unmarked frame. And you can see that it's got Y in there, it has our observation covariates and our site covariates. So it looks like it was processed correctly. So that's going to be the data that we pass on to these models. So let's start making some models. And it's a quick reminder that these models are kind of annoying. When you build an occupancy model in unmarked, you're going to have a little tilde, and then your site covariates, and then another little tilde, and then another piece of site covariates. And these are the 2 parts of the model. We're going to model P first and then psi. This is a little bit confusing because we usually talk about occupancy first and then P. I don't know why Unmarked has decided to make it different and backwards other than to make our lives complicated. But it's just remember that you're going to give the P formula first and then the psi formula. And if you look at your homework, the 4 models that we're going to run all have psi as constant. So we're not going to put any variables in the psi, so they'll all have this 1. Now, when you put 1 in unmarked, it does not mean that that is the value of that parameter. It just means that that parameter is constant or random. So the first thing we're going to do is we're going to create a model, and it's going to be the null model. So we're saying both occupancy and detection are constant. And so we'll run that. I've stored that model into a thing that I've called model 1, and we're going to now look at it. And you can see it has an estimate for occupancy and it has an estimate for detection. Because detection, non-detection data is binomial, it's a 0 or a 1, we can't use a regular regression model to model it. We have to use a generalized linear regression. We have to use a binomial. And so that requires a link function. And so what we use for 0, 1 data is called the logit link. And so these estimates are on the logit scale. So they're not inherently informative. We'll have to back transform them to get a probability, but these are our initial estimates of occupancy and detection. You'll see also that we are given an AIC value and the standard errors for each and the p-values for each of our parameters. So you're asked in your homework to run 4 different models, one where occupancy is constant, but the probability of detection differs by day of the week as a continuous variable, and that's what model 2 is. Model 3, occupancy is constant, but detection is influenced by day, and day is actually treated as a categorical variable there. And 4, occupancy is constant, but the lure used influences detection. So now that we have all 4 models made, we can do model selection. We can build an AIC table. So we're going to make a candidate list of the model. Don't worry about this red warning message. It just says that the models were unnamed, so they're just going to use the object names as names. And then we'll use the model selection function to create the AIC table. And what's the best model? By far, it looks like our best model is model 4. It has the lowest AIC. The next closest is almost 5 points away. And it has almost all of the AIC weight. So let's look at the estimates for model 4. What is that actual model saying? So this is the lure model. So occupancy is, so this is the logit scale for occupancy. But if you look down here, it gives us separate estimates for sardines and for tablets. So sardines have an estimate of 0.16, and remember that's on the logit scale, and tablets have an estimate of negative 1.485. Now these two things are both on the logit scale, but it's important to remember that these negative signs mean that it's a negative relationship. So tablets are worse at detecting cats than the sardines. Now to get an estimate for psi, for occupancy, that's not on that logit scale, that is on the scale that we want to think about it on that probability, we're just going to use back transform, which is a command that's within unmarked. And we're going to say, take model 4, and we want to know the state. That's that occupied, not occupied. And this is where you might change it if you have a different best model based upon your results. We'll run that, and then we'll look at it. And we see that the estimate for occupancy is 69, basically 70%, with a standard error of 0.153. So what was our initial estimate of occupancy was 60%, right? So this is actually about quite a bit higher. We've added almost 10% onto our estimate. So let's calculate a 95% confidence interval. So we're going to take the estimate of psi, which we just got. So that's 0.696, 0.696. Remember, you'll change this if you get a different estimate for your opossums and your raccoons. So we'll give psi. And then we're going to calculate the critical value. If you remember from your stats courses, when you have a standard error, to get your critical values, you want to, if you want to get 95% of the observations, you have to multiply it by 1.96. So you will not change this number. You will change this number if you have a different estimate of your standard error. So we'll calculate the critical value, and to get the upper 95% confidence band, we're going to add the critical value to our estimate of psi. So that's the critical value. We're adding it to our estimate of psi. And to get the lower band, we're going to subtract instead. And we're going to add the species name to help us keep track of these estimates. And so we're going to add the word cats. So we've created a little data frame. Now let's look at it. So we have our estimate of psi. We have the upper bound, which is almost 1. And we have the lower bound, which is about 40%. So that's your psi and your 95% confidence interval. So now we want to look at the effects of lure on P. And you cannot use back transform when there are covariates acting on your parameter. And so because we put covariates on P, we'll have to do it by hand. You are not expected to do this. You can give me just your logit estimates of P. You have to write down, of course, that it's on the logit scale. But you can give it to me. You can get extra credit if you go through these next couple steps and then give me P on the probability scale. So let's look again at our detection estimates. Our first sorry, I have a bit of problem in the code. From doing this before. Okay, so we're going to put the estimate of the effect of sardines. So that was 0.163. So I'm just going to copy that and put it up here. And then we have negative 1.485. And so we'll copy that and put that up here. So that's the logit of the sardines and the logit of the tablet. And to do the back transform, we're just going to undo the logit link. 2.7 is a mathematical constant called E, and it's basically the way that you undo the log transformation. And then you have 1 plus the undone log transformation, and that creates your proportion. So we'll do that for sardines and for tablet. And so let's look at our back transformed estimates for sardines. So it looks like we have 0.54 is P. So it looks like we have about 50% chance of detecting cats per night at sites with sardines. And for tablets, that answer is 0.18. So if there's cats using your site, you have a 0.18, almost 20% chance of seeing a cat walk past your camera if you're using a tablet as your lure. Okay, so we've gotten to the end of our first species, and so you are expected to repeat that with both possums and with a raccoon so that you get new estimates of psi and you get standard errors for both possums and raccoons. The second part of your homework is to make a graph. So I'm going to show you how to graph two estimates of psi together. So up here a little earlier, we created this estimate of psi in a 95% confidence interval. So all I'm doing is calling that back. There it is, right? It's psi, the upper and the lower, and it says that it's for cats. And now we're going to add a second species. Now, your estimates, your numbers are going to be different because you're going to do this with the data we collected. I just made these numbers up for to show you how to add a second species to your little data frame. So you're going to take the psi or occupancy estimate from your second model. In my imagination, it's 30. And I'm telling R to put it in the second row in the first column. I'm also going to add a critical value. So I'm thinking, or I made up, you will get this from the model, the standard error from the second model, and you're going to multiply it by 1.96, that standard to get the 95% CI. You're going to add it through your critical value to get your upper. You're going to subtract your critical value to get the lower. And then remember, we're going to add a name so that we can keep track. And so now we're going to look and see we've added possum in the estimates, the upper and lower estimate for possums to our data frame. So now we're going to make a plot. So we're going to load ggplot. You should not have to change any of this piece of, you will have to change a teeny bit of this piece of code. I'm not going to explain what all of these things mean, other than what it does is it gets your actual plot into JWM format. So it removes the boxes, it removes some of the lines, and it puts it into a nice way that can be exported and put directly into a paper that can then be accepted by JWM. So we're going to run this. And it pops up over here. So here we have the estimate for cats. Our estimate, remember, was about 70 with our 95% CI went almost to 1 and then almost to 40%. So it's pretty big confidence range, but we know that we probably have a pretty high occupancy rate of cats. And then we look over here at possum, and we know that possum has an upper bound of 0.37 and a lower bound of 0.22. And so it's got a much tighter confidence interval. So you must have had a lot better data on possum occupancy rates. But as you can see, these two 95% CIs do not cross. So we can determine from this analysis that cats and possums have a different rate of occupancy in natal. Excuse me. Okay, it's cat occupancy. So one thing you will need to do is just change your name. So, yeah, actually I will leave it as raccoon because you can just use this. So you will put your name right there so that this is unique to you, and I know that you must have at least gotten this far in your code. Once you have this, so I will just write my name. Okay, so there it is. It's SOVI, occupancy, possum versus raccoon, but it's actually cat. So I will fix that. And I will export this as an image. And you can name it whatever you want. I'm just going to name it Cat v. Raccoon. And then because we set our working directory, that picture will show up in our working directory. So what you will have to do with this graph is insert it into your homework assignment, into your Word document, and you will need to give it a title and a caption according to JWM format. The specifics for JWM format can be found. It's in the module section of Canvas. It's in that very first piece of in module that has general information for the course. All right, so enjoy your week of learning R. Please come to us. We know this is hard. We know that R has a very steep learning curve, and I'd be happy to go through the code with you. All right, have good luck, and I will see you guys on Thursday for your exam.